In this lesson, we give a brief introduction to the incredibly rich subject of heterocycles, introducing some of the more important saturated, aromatic, and bicyclic heterocyclic systems. A heterocycle is a ring that contains at least one heteroatom, or non-carbon. Heterocycles are immensely common in nature and among the most important organic structures. Here we see four rather simple heterocycles, some of which you've likely seen before. The first structure is an epoxide, a three-atom cyclic ether. Epoxides are important synthetic intermediates used throughout organic chemistry. Tetrahydrofuran, or THF, is a larger cyclic ether and is a commonly used polar aprotic solvent. 1,4-dioxane is a heterocycle with two heteroatoms and is also used as a polar aprotic solvent. Pyridine is an aromatic heterocyclic amine and is used as both a solvent and a weak base. The next two structures represent more complex, naturally occurring heterocycles. The first structure is caffeine, which, by the way, is the structure you see in the corner of each of these slides and at the start and end of each lesson. Caffeine is an example of a fused bicyclic heterocycle and is a stimulant found in coffee, tea, and various energy drinks. The second compound is nicotine, a stimulant found in tobacco leaves which has both saturated and aromatic heterocycles. As you might expect, saturated heterocycles contain no pi bonds within the ring. There are several systems for naming saturated heterocycles, and many important heterocycles have common names. In the naming system we introduce here, the parent chain is determined by the number of atoms in the ring, not carbons, but atoms. Let's first look at some important saturated nitrogen heterocycles. The first structure has a three-atom ring and is thus named as a cyclopropane. This likely seems really strange, given that the ring has only two carbons. The prefix aza is added to the parent name to indicate that one of the carbons in the ring has been replaced with a nitrogen. The name then becomes azacyclopropane, commonly referred to as an aziridine. 5 and 6 atom saturated heterocyclic amines are also quite common. In the next structure, we see a substituted azacyclopentane, commonly called a pyrrolidine. When numbering the parent chain using this particular naming convention, the heteroatom is given the 1 locant, making this compound 2-methyl-azacyclopentane. In the next structure, we see a substituted azacyclohexane, commonly called a piperidine. Because the substituent is on the nitrogen, the systematic name becomes N-methyl-azacyclohexane. Saturated oxygen-containing heterocycles are also quite common. The prefix oxa is added to the parent name to indicate that one of the carbons in the ring has been replaced with an oxygen. The first structure is an oxacyclopropane, more commonly referred to as an epoxide or an oxarane. The second structure is an oxacyclobutane, which has the common name oxetane. Saturated sulfur heterocycles are also somewhat common. The prefix thia is added to the parent name to indicate that one of the carbons in the ring has been replaced with a sulfur. Here we see an example of a thiacyclopropane, also called a thiarane. With respect to reactivity, saturated heterocyclic compounds react similarly to their acyclic counterparts. Cyclic amines react largely like acyclic amines. Cyclic ethers react similarly to acyclic ethers. Next, let's look at some unsaturated heterocycles, specifically aromatic heterocycles. There are 3 common 5-atom aromatic heterocycles that have only one heteroatom. Here we see pyrrole, furan, and thiophene. Because these compounds are aromatic, they can undergo the same electrophilic aromatic substitution reactions as benzene. Here we see thiophene subjected to an EAS halogenation reaction. Regioselectivity is a concern, and the reaction can result in substitution at either the 2 or 3 position. In the reactions of 5-atom aromatic heterocycles, substitution is mostly seen at the 2 position. If we look at the first step of the EAS mechanism, we see that attack at the 2 position leads to a more stable intermediate with 3 resonance structures. Attack at the 3 position leads to a less stable intermediate with only 2 resonance structures. The regioselectivity is therefore kinetically controlled. The more stable intermediate formed from attack at the 2 position results in a faster reaction, producing more product. With respect to overall reactivity, it turns out that pyrrole, furan, and thiophene are all more reactive than benzene in an EAS reaction. The exact reactivity order is shown here. There are several factors that lead to this order of reactivity. Pyrrole, furan, and thiophene are all less aromatic than benzene, making them less stable and thus more reactive. We can see why when we compare the pi molecular orbitals of benzene to thiophene. Using the Frost circle method, we see that the pi-bonding molecular orbitals of benzene are simply lower in energy than those of thiophene and the other 5-atom aromatic heterocycles. This makes the pi bonds of benzene stronger, making it a more stable, less reactive compound. To understand the relative reactivities of the 5-atom aromatic heterocycles, we need to look at the intermediates that form after the first step of an EAS reaction. Here, we see the intermediate resonance structures that have both a pi bond and a positive charge on the heteroatom. Due to its lower electronegativity, a positive charge placed on a nitrogen is more stable than one placed on an oxygen. This makes the pyrrole intermediate more stable than the furan intermediate, leading to a faster reaction for pyrrole. To see why thiophene is less reactive than pyrrole and furan, we need to compare the qualities of the carbon heteroatom pi bonds. The CN and CO pi bonds in the pyrrole and furan intermediates are quite stable. In each case, the pi bond is formed between a pair of 2p atomic orbitals, leading to a fairly good overlap and thus strong pi bonds. However, the CS pi bond in the thiophene intermediate is formed between a 2p orbital on carbon and a 3p orbital on sulfur. This mismatch in orbital size results in poor overlap, leading to a rather weak pi bond. The intermediate formed from thiophene is thus considerably less stable than those formed from pyrrole and furan, leading to a slower reaction for thiophene. There's really only one common 6-atom heterocycle that has only one heteroatom, and that's pyridine, a 6-atom aromatic amine. Because pyridine is aromatic, it can undergo the same electrophilic aromatic substitution reactions as benzene. Here we see pyridine subjected to an EAS halogenation reaction. The reaction can result in substitution at either the 2, 3, or 4 position. In the EAS reactions of pyridine, substitution is mostly seen at the 3 position. If we look at the first step of the EAS reaction mechanism, we see that attack at the 2 or 4 position leads to a less stable intermediate in which one resonance structure places a positive charge on the electronegative nitrogen. Attack at the 3 position avoids placing the positive charge on nitrogen, leading to a more stable intermediate. The regioselectivity is kinetically controlled. The more stable intermediate formed from attack at the 3 position results in a faster reaction, producing more product. Pyridine is considerably less reactive than benzene in an EAS reaction, and often requires more vigorous conditions. This is in part due to the electronegativity of the nitrogen atom in pyridine, which pulls in electron density, making it less available for nucleophilic attack. Pyridines that have a halogen or other good leaving group can also undergo nucleophilic aromatic substitution. The reaction is fastest when the leaving group is in the 2 or 4 position. Here, we see 2-chloropyridine undergoing an SNAR reaction with methoxide. Unlike SNAR reactions of benzene, a similar reaction of a substituted pyridine does not require a nitro group to facilitate the reaction. The electronegativity of the nitrogen atom is sufficient to stabilize the negative charge in the intermediate formed after nucleophilic attack on the halogen-bearing carbon. We'll wrap up our brief look at heterocycles with a short introduction to bicyclic aromatic heterocyclic compounds. The structures we'll be looking at each involve an aromatic heterocycle fused to a benzene ring. A 5-atom pyrrole ring fused to a benzene becomes indole. A 5-atom furan ring fused to benzene becomes benzofuran. And a 5-atom thiophene ring fused to benzene becomes a benzothiophene. The indole system is particularly common in nature and is found in several biologically important compounds such as tryptophan and serotonin. A pyridine ring can be fused to benzene in 2 ways, forming either quinoline or isoquinoline. Both structures are common in nature. The quinoline system is found in quinine, an alkaloid drug used to treat malaria. Because these systems are aromatic, bicyclic aromatic heterocycles can undergo EAS reactions. If we look at the first reaction, we see indole subjected to an EAS bromination. The reaction can result in 7 different monosubstitution products. Determining the major product in this case is straightforward. We know that pyrrole is more reactive than benzene in an EAS reaction, so the reaction will be faster on the pyrrole ring of the indole. We also know that EAS reactions of pyrrole favor substitution at the 2 position. We can thus predict that the bromine will be introduced preferentially to the 2 position of the pyrrole ring of indole. In the second reaction, we see quinoline subjected to EAS sulfonation. We know that benzene is more reactive than pyridine in an EAS reaction, so the reaction will be faster on the benzene ring of quinoline. In this case, regioselectivity within the benzene ring is rather complex and beyond the scope of this lesson, and the reaction proceeds to give a mixture of regioisomers.